So what we're going to talk about today actually is a big part of two of the parts of Enduring Understanding 1D. 1D1, we were talking about different models of the atom and the evidence that led us to overturn a certain model and come up with a new model. So we talked about those laws, definite proportions, multiple proportions that led to the creation of Dalton's billiard ball model. And then we talked about the cathode ray tube experiments and how by measuring the mass to charge ratio of these cathode rays and trying different materials and finding that that ratio is constant, that Thomson discovered that all atoms were made out of little particles that we now call electrons. So then I also mentioned the fact that J.J. Thomson went on to discover the process of mass spectrometry, which is to use an electric field to move isotopes, curve the isotopes in a certain way that we can actually see differences in their mass. And if you go down to 1D2, it actually talks specifically about mass spectrometry. So that's another reason I really want to focus on this and make sure you guys understand what this data is telling us. So it says an early model of the atom stated that all atoms of the element are identical. That was Dalton's billiard ball model. Mass spectrometry data demonstrate evidence that contradicts this early model. So what is mass spectrometry? So we started by looking at, this is all sort of on the big idea notes as well. I showed you guys this picture yesterday, but I'm not super crazy about this picture. So I want to kind of simplify it for you guys on the board. Basically what we have is we have some sample that we put into this machine. And we have to do two things first to the sample. First, we have to turn it into a gas. We have to heat it up till it vaporizes because we're going to send it through the machine. And we don't want to send it as like chunks of solid, we want to send it as individual atoms. So we got to vaporize it. And then we have to ionize it. So usually there's some sort of electron beam that the electrons go through, they smack into these atoms and knock electrons off of those atoms. So what we end up with after this step is a bunch of positively charged gaseous ions that we can send into our detector. Now, we have to accelerate these ions, so there's some plates here that talk about accelerating these things. We have to get these things moving. Once we get these things moving, though, we basically want to create some sort of field. It has a magnet here. It could be a magnetic field. It could be an electric field as well. So if we set up an electric field and we make one plate of this thing positive and one plate of this thing negative, then we know these ions are going to change their path. Right? They're going to be repelled by the positive part, attracted by the negative part. And so if they come in traveling this direction, they're going to change their course, right? So the ions are going to come in, and then they're going to change course. And somewhere on the other side of this field that we've set up to change their course is some sort of detector. I just made a little bucket. It's not really a bucket. Usually what it is something that when these positively charged ions hit it, it creates some sort of current. So it creates some sort of electrical signal. All right. And what we do is as we send these things through, if this sample is a mixture of different mass particles, those particles, as they're accelerated through the field, they're going to come in here with different momentums. So heavier particles have more momentum, right? It's harder to stop a big, heavy truck in an accident than it is to stop a little bike, right? So these things are going to curve. If it's a mixture, they're going to curve by different amounts, and the amount that they curve is going to depend on their mass. Okay? So if we have some heavier atoms in there, I want to do those same color as the detector. So let's say we have some heavier ones in blue. The ones in blue are going to curve by a different amount, and so at whatever field strength I've set up, at whatever strength this electric field is, one type of particle might hit the detector, the other part might not. Okay? When we make this field stronger, I can get these blue ones to curve into the detector, and the black ones will curve too much, right? They'll hit over here and not even touch the detector at all. Okay? So that's the basic schematic of how this mass spectrometer works. So we have a simulation here that I linked to on the notes. And we basically have a similar kind of idea, right? Except here they're using magnetic field. You guys remember in physics, isn't B the symbol for magnetic field? And I can do things like I can vary the strength of the magnetic field here. It's in Teslas. Okay, so I can have a really strong field. I can have a really weak field. I'll start somewhere in the middle. And I can actually change the speed of the particles. So how fast they're coming out of that accelerator. How fast they actually fly into the detector. So let's put this sort of a medium level. Okay, so this is my sample right here after they're getting shot out of that accelerating field. And we'll look at uranium. If I turn uranium-235 on, it has some mass here. I run the detector, and it hits at this point right here. If I reset and load it with uranium-238, it also curves. You might not be able to tell from where you're sitting, but it curved just slightly less. It actually hit a little bit further down. Let's see, it says 44.37 here for uranium-238. What did it say for uranium-235? 43.808. Okay? Uranium-235 being lighter is more strongly affected by that magnetic field. Right? It has less momentum, so it can curve more. Now, both of these are curving too much, so I want to totally change this thing. I want to make the field a lot weaker, and I want to make the particles a lot faster. So now when I run, okay, the uranium-235 goes 204.75 centimeters. Uranium-238, 207.375 centimeters. Okay, so again, you can see that by adjusting how fast the particles are going and how strong this magnetic field is, I can control where the particles land. Okay, so essentially what this mass spectrometer is going to do is it's going to have a detector that doesn't move, and it's just going to crank up the field until the particles, well, I guess if they start here, it's going to crank up the field until the particles get closer and closer and closer, and eventually they'll drop in the detector. Okay, but just like I explained here, because the particles have different masses, if the detector is small enough, one type of particle is going to hit the detector and cause a signal, and the other particle is going to hit somewhere else. And then if I make the field just a little bit stronger, then I might be able to get the other type of particle to hit that detector, and I'm going to see another signal. Okay. I think I talked about yesterday an example of this in World War II, the Manhattan Project. So I looked it up. This was called the Y-12 project. There are three ways that they tried to separate the uranium-238 and the uranium-235. The uranium-235 is the one that they wanted. So this one was done in Tennessee, and the uranium that they produced actually was used in the bomb that we detonated over Hiroshima. They shut it down after the war because the other methods tended to be more efficient, okay, but like, look at the size. That's like a guy standing here, and this is just one of those little, it's basically a mass spectrometer. So they feed in the uranium mixture in here, and they've got a big curved setup here with electric fields in there, so that when those particles traveled through that electric field, because they had different masses, they would collect at different places. This article is really interesting if you read through it. What they found, they were training people to try to kind of control the dials that worked this machine. And so I had these scientists that were trying to control the dials, and they were trying to make sure everything was just right. Then they found some, it turned out they were mostly women from the area around Oak Ridge, Tennessee, and they trained them. They didn't tell them anything about what they were doing or how this process worked. They just said, try to make sure this dial stays in a certain spot. And what they were trying to do is to make sure that the dial was kind of as high as it could, representing the most particles dropping into their little detector bucket as they could. And they found out that the women who had no idea what was going on did a better job of keeping that dial where it needed to be than the scientists, because the scientists always wanted to stop and figure out, oh, why did it do this? You know, what is causing this little change? And the people that had no idea of what was actually going on were just trying to keep that dial where it needed to be, and that ended up being the most efficient way to do it. So this is kind of cool. I just thought it was an interesting application if you're curious about reading about those things. This is the huge setup that they had. You can see the ladder for scale here. Somebody would be walking up this ladder to get on top of this thing. And when you read the article, they said they used about $1 billion worth of silver from the U.S. Treasury. $1 billion back then.
That's a lot.
There's a lot of silver. Yeah. There's an interesting story in the article that talks about one of the guys from the Manhattan Project going to like the Secretary of the Treasury and saying, I need 6,000 tons of silver. And the Treasury Secretary says, how many troy ounces is that? He's like, I have no idea. Because they didn't know what he didn't know what the conversion was between troy ounces and tons, because he's a scientist, right? And the guy goes, well, I need to know how many troy ounces. He's like, it doesn't matter, it's 6,000 tons of silver. Okay, so there's $1 billion worth of silver that they used. They actually made like 3 different versions of these things by the time the war was done. All right, so now we have a sort of general idea of how the thing works. Let's look at what the data looks like. So this link that I put on here is a little simulator that's going to show us what mass spectra actually look like. So if I put in uranium, for example, and I hit calculate/plot, it shows us what the plot of the mass spectrum of uranium looks like. It's super boring. Just see spikes. Kind of for the same reason we saw spikes in the PES spectrum, right? We changed the strength of the field that was curving those electrons, and we saw nothing, 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 and then we hit some certain strength that curved electrons into the detector, and we saw a spike. And then we saw nothing, 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 and then we hit a different strength of the field that curved the electrons. That caused a different type of electron that had a different kinetic energy to hit the bucket, and we saw another spike. Right? And what was the height of the spikes telling us in PES? How many electrons the detector was detecting? Or really the relative number, right? If you go back and look at those y-axes, it never says how many electrons. It says the relative number, right? The detector might detect 2 billion electrons at one particular spot, and then it might detect 6 billion electrons at another spot. Okay? It doesn't know how many atoms those electrons came from, so it's basically just saying, by the relative heights of them, the relative number of electrons that are coming from each of those subshells. So this is telling us something as well, right? You see a very, very small peak here. We see a much, much larger peak over here. And if we look at the x-axis on a mass spectrum, we see that it says m over E. Remember, that's what Thomson was studying in the cathode ray tube experiments, studying the ratio of the mass to the charge. Why did they do it as mass over charge instead of just mass? Because it turns out when you ionize these atoms, sometimes you're going to knock 2 electrons off. You might doubly ionize this atom. So I drew these too small to show this really well, okay? But if I make a 2+ ion in here, if I send a 2+ ion through this same field, what's going to happen?
It's going to curve a lot more.
It's going to curve a lot more, right? Coulomb's law says the bigger the charge is, the more the force there's going to be, right? So these 2+ ions might actually curve a lot more, and so you'll get a signal for the same mass of atom at 2 different points. You'll get one corresponding to the +1 ion, you'll get one corresponding to the +2 ion. You might even see a really small signal for a +3 ion, although it's not as likely. We know the ionization energy gets larger and larger every time we remove electrons. Okay? So if we see a signal at 235 corresponding to one type of singly ionized uranium, we'll see another spike at half this, which is 167.5. Is that right? Get out your calculators. You're going to need them out anyway. Now the whole 2+ thing, I doubt they're going to give you any examples where you see peaks from a +1 and a +2 situation here, but I just wanted to point out that's why this axis isn't just mass, it's actually mass over the charge. Okay, so as long as we know we're looking at the +1 ions, then it's the true mass over a charge of +1. It's really telling us the actual mass of this thing. So first thing we're seeing is that one of the types of atoms in this uranium sample has a mass of 235.04393. Whatever. It could be atomic mass units, right? If we're talking about individual atoms. All right. Over here we see another signal at 238.05079. These are 2 different isotopes of uranium. What are the 2 isotopes? Well, when we write these symbols to distinguish different isotopes, how do we show a lighter isotope of uranium from a heavier isotope of uranium? You guys remember how to write isotopes?
We should put on the top right.
Top right?
It was written on the left. So probably the left.
Context. On the top left. So we write one type of isotope here, but what is it that we write up here? What number do we put up here?
Atomic weight.
Number of neutrons.
Atomic weight will be 235.04393.
Number of electrons.
Number of electrons in a neutral atom is the same as the number of protons.
Number of neutrons.
Number of neutrons depends on the isotope. Would be actually probably smart if we'd have gotten in the habit of just writing the number of neutrons up there, because we know we can find the number of protons by knowing what element it is, right? But it turns out we make it a little bit more complicated. What we write up here is called the mass number. We write the total number of protons and neutrons. So if you remember back to your first chemistry class, you had to use that mass number and you had to look up the atomic number, then you had to subtract the atomic number from the mass number to find the number of neutrons. What is the mass number of this isotope? 235. It turns out in almost all cases, the mass number, the total neutrons and protons, is very, very close to the atomic mass in AMU. It's usually going to be either a 0.0 something or something 0.99 something or 96 something. So if you round to a whole number, that's usually going to give you the isotope number. So we've got uranium-235 in this sample. And what's the other isotope?
238.
Uranium-238. Why don't we see uranium-236, uranium-237?
They're not common.
They don't exist really.
Not
Why?
Because
They do exist, but not in our sample because they decay very, very quickly. It is possible to create uranium-236, but it doesn't stick around very long. So when we dig up uranium out of the ground, there's not going to be any uranium-236 in there. Any uranium that was 236, any that was produced in the supernova explosion that created all the mass that eventually turned into the Earth is long gone. Long, 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 long gone. Okay. So usually what you're going to see in these mass spectra, unless you put some artificially produced thing in there, you're going to see just the longest lived or naturally occurring isotopes. All right, so if we scroll up a little bit, this thing actually tells us some more information. On this y-axis, we've got the relative intensity. We see this one is pretty high, close to 100, and we see this one is really low, but we don't know what the values are. If we scroll up, there's a data table up here, and the data table tells us the values. It says that the uranium-235 peak had an intensity of 0.7, and the uranium-238 peak had an intensity of 100. What does that mean? That means whatever number of uranium-238 atoms hit the detector, that was the biggest signal that it saw. So it calls that 100. There's always going to be a peak on this spectrum that reads 100. Because the machine doesn't know how many atoms are hitting there, it just sees some sort of electric signal. It says, ooh, that was the strongest signal, I'm going to call that 100. Then it saw another signal corresponding to this ion, and it's telling us compared to the strength of this signal was only a 0.7. Okay, so one of the first things we're going to have to do is to figure out, based on this data, what percentage of the atoms that we put into this machine are uranium-235, and what percentage were uranium-238. It's called percent abundance. You guys remember hearing that term? So if we have multiple isotopes for an element, we can say what percentage abundant each isotope is. What percentage of all the atoms of uranium are uranium-235? What percentage of all the atoms of uranium are uranium-238? Now we can't just use these numbers. Why not? They're relative intensities. If I say that this one is 100% of the atoms, how could this be 0.7? That would add up to 100.7, right? That's more than 100% of the atoms. So what we have to do to calculate the percent abundance is we have to take the strength of the signal for the isotope we're talking about, and we have to divide it by the strength of all the signals that we see. So for uranium-235, we're seeing a signal strength of 0.7. We're going to divide that by all the signals, which in this case there's only 2, 0.7 plus 100. Now to turn it into a percent abundance, we got to multiply by 100. And what do we get? .695. We've only got one sig fig here, so we actually get 0.7%. If we do it for uranium-238, the signal for uranium-238 was a height of 100. The totals is 0.7 plus 100. What do we get? 99.3. Andy, is that what you got?
Yep.
Yeah. Jess?
If you only have one sig fig, are you supposed to say?
Yeah, so this thing has got a little bit of issues with sig figs, right? They're technically only giving us one sig fig here. Well, I guess if we know how mass spec works, we know this has got to be exactly 100, right? But yeah, they're only giving us one sig fig here, so it's a little bit weird. So this is maybe not a great example for how to do this. So let's pick a different element. Oh, wait, before we do that, let's look at Wikipedia's table of all the isotopes of uranium. Notice we've got on this isotope table uranium-215. That's the first one we see. Why didn't we have a signal at about 215?
Too small.
Okay.
Yes, uranium-215 has a half-life of 2.24 milliseconds.
Nice.
So before you even dug their uranium out of the ground, if there happened to somehow be any uranium-215 in there, it wouldn't be there anymore. It would have turned into something else. It would have decayed into thorium-211. Okay. Ooh, this is interesting. Nuclear spin. Remember we were talking about MRI and how it takes advantage of nuclear spins. Okay. But if you notice here, under the representative isotopic composition, there's no value there. There's no value because the stuff doesn't stick around. Okay. If we scroll down to the isotopes we actually saw, uranium-235. Ooh, actually uranium-235 is not 100% stable. But look at its half-life. 7.04 times 10 to the 8th years. What's that?
A long time.
It's a long time. 700 million years? Okay, so you dig that up out of the ground, you bring it to your detector, it's still going to be in there. All right. If we scroll down to uranium-238,
26 minutes.
uranium-238 is technically not stable either, but it has a half-life of
Another
A long
long
time.
almost the age of the Earth. So whatever uranium-238 was present on the Earth when it formed, at this point, half of it's gone. It's decayed into something else. After another 4.6 billion years, half of that will have decayed into something else. Okay, but these are the two longest lived isotopes, so they're still going to be around for us to measure. And if we go to their representative compositions, we have 0.9927, which is 0.993, which is this as a fraction. Right? We've got 0.007204 up there as the fraction for uranium-235, which is what we found. Okay, so that's how we know these percent abundances. We put pure samples into these mass spectrometers, and we've measured how much of each isotope there is. All right, somebody give me a different element.
Copper.
I was gonna say, don't everybody shout out an element at once. You guys are gonna make for a very interesting video when somebody watches this. I think. You'd be like, did Mr. Ball just like put up a bunch of cutouts in the chairs to make it look like there were students? All right, good example. Woo! Copper. Boom. So from this, we can actually tell how many isotopes of copper are there. How many stable isotopes?
Dose.
2, assuming I scroll over and there aren't any more. Yep, just 2. And which 2 isotopes are they?
63, 65.
Uranium-63, be careful, right? This is 62.92, so we got to round to the nearest whole number. So copper-63 and
65.
copper-65. Apparently copper-64 is not stable. So copper-63 and copper-65. Which one is more abundant? 63, right? Because we can see the signal for copper-63 is larger. So in any pure sample of copper, we're going to have more copper-63 atoms than we have copper-65 atoms. Can you estimate the percent abundances from this?
Yeah.
So like
50 and 100.
50 and 100?
Yeah.
You add those percent abundances together. Not the relative abundance, the percent abundance.
Oh.
This is where you got to be careful. And this would maybe be a question they would ask on multiple choice. And one of the things is going to be, yes, their percent abundances are 150. But we know that 150 can't be the percent abundances, because if we add those together, we get 150%. These are the relative strengths of the mass spec signals. Well, if one is 50 and the other one is 100, what's the total? 150, right? And so if this one is 100 out of the total 150, about 66%, right? So that would be a good multiple choice question to see if you really understand how these calculations work. All right? Well, let me go up there to the data table. And here's the actual numbers. Let's calculate the percent abundance of these two different isotopes. You gonna remember this run? Oh. What'd you get?
For the first one, I got 69.15%. And the second one, I got 30.84.
Agreed? You rounded up to 0.16?
I
I just said 74.
Yeah, we know these things should equal 100, so yeah, that's the first thing I saw. 5 here and a 4 here is going to add to that. Okay. All right. So, anybody not get that? Going once? Going twice? Okay, if we look at the table on Wikipedia, we get 0.6915 for copper 63, 0.3085 for copper 65. So pretty close to what they have. On this last column, you can see kind of interesting, there's actually some variation depending on where you get the copper. This is the naturally occurring variation. So it could be as low as 30.66% copper 65. It could be as high as 31.017% copper 65. Depends where you get it. Did I tell the story of Utsi?
What determines that variation?
What determines that variation? Ooh, that's a fantastic question. For copper? I don't know. It's possible that because they have different masses, maybe in the mixing process, and there is crust or something like that, they differentiate slightly, and so maybe you get one pocket somewhere in one part of the crust that's different. I don't know. But did I tell the story of Utsi in this class?
Nope.
You know who Utsi is? Did you fall asleep? You were struggling. Utsi the Iceman? You guys never heard of Utsi?
That's my boy.
Okay. This is someone they found, some hikers were actually climbing in the Alps, and they were climbing on this glacier, and they saw this dead body laying there, and they're like, oh my gosh, somebody got murdered. And so they called the authorities came out, and when they started digging this guy up, he was like half in the ice. When they started digging him up, they're like, this is something not right here. It turned out this guy lived like 3,000 years ago. No, sorry, 3,000 BC, 5,000 years ago. He was murdered on top of this glacier, and he happened to fall in this area of the glacier. Snow accumulated on top of him, and the glacier actually built up over him and was like, you know how glaciers move over time, right? He just happened to be stuck in this perfect pocket of the glacier that the glacier went right over for 5,000 years. So climate change, glaciers started to melt, and eventually his body was uncovered again. He was so well preserved that they could actually go inside of his stomach and take out what he had eaten on the day he died. Which is really interesting, because if you run the material that was in his body when he died, if you run it through a mass spectrometer, you can separate out the different components that are in his food by their mass, and you can actually see differences in the isotopic composition of his food. And because different elevations have different amounts of certain isotopes of carbon in them and oxygen and things like that, they can actually get an idea based on this analysis of where he lived, what he ate, right? They can analyze his teeth and the types of isotopes that got, preserved in his teeth as they were growing. They got a lot of information about what his life was like, even though he lived and died 5,000 years ago. So this is pretty crazy if you want to read about Utsi, the Iceman. I actually found a link, well, somebody sent it out. This link right here is about mass spec as well, and it tells a little bit more about what mass spec can be used for. And this talks a little bit about mass spectrometry on molecules. It turns out it's more complicated when you start to put molecules through a mass spectrometry, because molecules are combinations of atoms, and each atom can have different isotopes. So if we go back to our mass spectrometer simulation, even if I run a simple compound like H2O through here, H2O, we only see two major peaks. Let's look at CH4. That's kind of... CH4, I see three peaks. One with a mass of 16.0313, and two pretty close to a mass of 17. Well, if we think about CH4, right, carbon's supposed to be 12.01, hydrogen's supposed to be 1.008, so this is like the normal atomic or molecular mass of CH4, right? What the heck are these? Well, the normal one is CH4, where you have carbon 12 with hydrogen 1s attached to it. Those are the most common isotopes of those atoms. But you can have, instead of carbon 12, you can have a carbon 13 in this molecule. So if you have a carbon 13 attached to a bunch of hydrogen 1s, it's not going to weigh 16 anymore, it's going to weigh closer to 17. Okay? But you can also have carbon 12 attached to a bunch of hydrogen 1s, but you could have a hydrogen 2 in there. Heavy hydrogen. What's this going to weigh? Pretty close to 17 as well.
What makes an atom heavier again?
Different numbers of neutrons. Yeah, good question. We talk about the difference between carbon 63 and copper 63 and copper 65. How many protons does copper have?
29.
29. I was going to pull the periodic table out, right? So sometimes you'll see 29, the atomic number written here. If you want to know the number of neutrons, you just subtract. 63 minus 29?
35.
34.
34.
34, okay. So 34 neutrons in copper 63. 65 minus 29,
36.
36 neutrons.
Do
They
neutrons-
differ in the number of the neutrons.
Do
What?
they do anything?
Do what?
Do neutrons like do anything?
Sure,
What do they?
they do lots of things.
Like you never hear about those. Like you always like you're like electrons are negative and they like.
For chemistry, the electrons are the most important. In chemical reactions, all that really matters is the electrons, because those are the things that we're sharing, the things that we're transferring, and stuff like that.
And like protons are special because that tells you like what it is.
True.
And then the neutrons are just like there.
So the neutrons are actually hugely important, because if we think about a nucleus, if a nucleus is a ball of protons, what's the charge on a proton?
Positive.
Positive. How does a ball of little positive charges stick together? Can't, right? Because we know from Coulomb's law that positive charges will repel each other. So the neutrons are actually in there to help hold the nucleus together. Now the neutrons do not have a charge, so how do they, if they don't have a charge, keep those protons together?
Magic.
Turns out we've only talked about one of the forces of nature. Coulomb's law only describes the force between charged particles. We call it the electromagnetic force. We've been talking about electromagnetic waves of light, the electromagnetic force. Okay. Another main force you guys have heard of before?
Gravity.
Gravity. Keeping your chair right now, right? Those are two of the four main forces in nature, right? The other ones are the strong and weak nuclear force. So neutrons attract to protons by those nuclear forces, which counteract the repulsion that those protons would feel from the electromagnetic force. So if the neutrons weren't in there, protons wouldn't be stable. And actually what's interesting is the reason we only see certain isotopes that are stable is that we have to have sort of this perfect ratio of protons and neutrons in the nucleus to actually make that thing stick together. If we throw that ratio off, the neutron becomes unstable, and then what it does is it spits out some particles to turn into something else that has a better ratio. Unfortunately, I don't think we really talk about nuclear decay at all in AP chemistry. Did you guys do it in regular chemistry? Beta decay, alpha decay, things like that? You wrote those equations, you had to balance the mass numbers and the atomic numbers.
We don't do that.
Why? Because technically that's not really part of chemistry. That's really physics, nuclear physics. Some people call it nuclear chemistry as well, but you know, it's just not really something that most people are going to encounter every day, especially as a chemist. Unless you're really focusing on nuclear, you're not going to even have to worry about it. So it's unfortunate. Okay. One last thing I want you guys to be able to do. The last thing you may be asked to do is to calculate for a particular element what is its average atomic mass. So I want to do this for copper. How do we get those numbers that are at the bottom of copper on the periodic table? Did I give you the equation for average atomic mass? It's a weighted average. Because when we look at copper, we don't see equal amounts of these two isotopes. So the weight of copper 63 is not going to count the same amount as the weight of copper 65. If it was like that, we'd just divide the two, we'd get something close to 64, right? But remember, we did a number line, I think, at one point. So if we have copper 63 and copper 65 are two isotopes, what's the average on the periodic table? 63.5? I'm looking behind you. Copper, yeah, 63.5. So if the average is about here, what does that mean?
There are more 63s.
We have more copper 63 than we have copper 65, right? In fact, that's what we calculated right here. It's about 70% copper 63 and 30% copper 65. Okay? But how do we calculate those averages? So we use the equation. The average atomic mass is equal to the sum, you guys all familiar with this symbol? The sum of what I'm going to call the isotopic masses. That's these numbers right here. That's what the isotope actually weighs. Some people, if you took regular chemistry, your teacher might have taught you to calculate average atomic mass using the mass number. You will get close to the right answer. But to get the actual number, you have to use what the isotope actually weighs. So IM stands for isotopic mass. And we have to multiply those isotopic masses by their fractional abundance. So we want to convert the percent abundance to a fraction, and then we multiply it by the isotopic mass, and we add them up. We take the sum of all the isotopes that there are. So let's do that for copper. Well, our first isotope has a mass of 62.9296. That's in atomic mass units. Its fractional abundance, what's that?
6916.
Yeah, we got to take its percent abundance, 69.16%, and divide it by 100, and that would give us the fractional abundance, 0.6916. Then we'll add to that the other isotope, which weighs 64.92779. We got to multiply by its fractional abundance, which is 30.84%, divided by 100. Get out your calculators. Jess, is that what you got? Anybody else get 63.54? Which is what it says on the periodic table. 63.546 under copper. Okay, so they might ask you to do that. They might ask you, given this data, tell me what the percent abundances are, and then if we tell you what the isotopes weigh, tell me what the average atomic mass would be. Smells like a great quiz question. So on the problem set that I'm going to give you, you are going to have to do those calculations. All right? Questions? Yeah, we're going to take a break. Go ahead, get up, stretch, use the restroom if you need to.